So we're going to look today about generating sequences. This is of a special importance since Lab 6 has to do with generating sequences. So the idea is you've got a language model and you want to actually use that not to make predictions or classifications or regressions, but instead to generate text. Okay? So for instance, you might have a language model that has been trained on Shakespeare, for instance, and you might then provide some sort of a prompt that says, give me something that sounds like Shakespeare that starts with why is life, and then we'll let it continue on from there. Does the problem make sense? So we provide this prompt, and then we're going to have the language model generate. How will we know? Well, let's just even back up a second because we haven't really looked in detail on how to do that. So we're going to have our RNN. Right, so our RNN will be here. What will we use as X1, X2, X3? So this is our trained RNN language model. Yeah, so X1 is going to be why, X2 will be is, and X3 will be life. We're going to feed these all into the recurrent neural network. What are we going to feed in as H sub 0?
I guess it'll be 0, right?
Yeah, we're going to feed in zeros here because we're at the beginning of a sequence, right? We have no memory we want to keep track of. And then if we look at the y hats, right, we have coming out of here y hat 1, y hat 2, y hat 3. Actually, I lied about something. So we're not going to provide x1, x2, and x3 as y is life. We're going to actually provide 4 inputs. What's that 4th input bin that we might want? So I'll help you out here. This is going to be x4, x3, and x2. What we'll actually put in is some beginning of sequence, right? Remember, as we were doing the training, we had, and you may remember that FastAI does this, right? It puts a special token at the beginning of every sequence to say, hey, I'm starting fresh. And so we want to go ahead and put that in so that we are simulating, as we're generating, the same things that we're trained on. So when we're trained on the beginning of sequence, and then we put our 4 words. So we're going to actually get 4 outputs, y hat 1, y hat 2, y hat 3, and y hat 4. Jessica, what does y hat 1 represent?
It would be like it would be x2, or like given x1, what would
Given
it be?
x1, which is beginning of string.
And then what would be like the prediction of x2?
The prediction of x2, that's right. So it would be a prediction of what word starts a sequence. Do we care about what it predicts, though, for what x2 is going to be? We already know. We know we're going to be using y. So we don't care about y hat 1. We don't care about y hat 2. We don't care about y hat 3. What's y hat 4 represent, Jessica?
The word afterlife.
The word afterlife, do we care about that?
Yeah.
So this is what we're going to be looking at, this y hat 4. And it's going to be a bunch of probabilities, right, for every word in our dictionary. So unfortunately, my example over here is not quite matching up with my words here, but that's fine. Let's just say we had a different prompt for a moment. So let's say the prompt was It actually doesn't matter. So let's just go here and then look at basically what we've got is a bunch of probabilities, right? So I just made up an example where I has a probability 0.4 and he has a probability 0.2 and C 0.1 and Y 0.0001 and there's a bunch of other words here too, right? And then if you think about it, if I were the next word, then there'd be a bunch of probabilities for all the other words below that, right? And then if we choose gave, so it was Y is, this doesn't really make a lot of sense, does it? Y is life I gave. Then there'd be a bunch of probabilities below that and a bunch of probabilities below that. And it's this huge tree with a high branching factor. We haven't yet determined how we're going to be navigating this tree. Okay, so we haven't set what we're going to actually do with y hat 4, but conceptually we do have this tree. What are the leaves of a tree, Jared?
It should be the end of the sentence.
Yeah, end of sentence or end of sequence, let's just say. So somewhere down here, we're going to end up with some end of sequence. Well, in fact, there's an end of sequence everywhere in here, right? It's just in some places in the tree there might be lower probabilities, and in other parts of the tree there might be higher probabilities. So we'd expect when you got the end of a complete thought that that would be a good place for an end of sequence. And we'd expect that y is life, we would expect that the end of sequence would have a very, very small probability because we don't just want to stop right there. Questions at this point?
These branches, so whenever we predict a word, do we get like this huge tree kind of thing?
Well, what's going to happen? That's a good point. So how do we actually generate this tree? There's not the entire tree like anywhere in memory. That doesn't exist. Instead, what happens is we feed in some input and we get one level of the tree, right? One part of this subtree and all these words. And then we choose one of these words, and I'm going to go over this in detail, but we feed that into the RNN again, and then we get a new y hat. And that then gives us the probabilities for everything below that. And then we choose one of those, and that gives us this. So where the subtree is revealed to us as we choose a particular word and feed it into the RNN. So let's try an example. First off, let me change these words here so they make more sense with this y is life. So y is life, I'm going to have to make this up a little bit. And theoretically, I'm also imbuing this with some Shakespeare too, but we'll see how this goes. So let's say y is life so. Okay, so has a probability of 0.0. Y is life, let's just say very. Y is life also, I don't know. And then so, let's say we have hard here. So full. Y is life very. Let's say this one is, I don't know what this is, but this is very difficult. Okay. If we had this whole tree somehow in front of us, what would be the very best ending of y is life? How would we, there's lots of different paths through here. Which path is absolute best? Which would be the very best path through this tree? How would we determine that?
We determine based on the maximum probability in each branch going down.
Maximum probability in each branch going down. Okay, so that's one possibility. So let's look at that. In that case, we would say, assuming this was all the probabilities, these were all the highest probabilities, so would be the best choice because that was the highest among here. And then hard would be the best choice here, assuming nothing else is bigger than 0.2. And then we keep going down, picking the highest at every choice. So at every branch, we choose the highest possibility of the probabilities in there. And we keep going until eventually EOS, right, end of string must be the highest probability. Does that correctly describe that, Tom?
Yeah, I think so.
Okay. That would be what we'd call a greedy search. And really what we think of it, what we're doing is searching through this tree. Now when we say greedy, sometimes greedy algorithms give you the optimum result, right? But do they always?
Wait, say that again?
Do greedy algorithms always, are greedy algorithms always optimal? Or are there cases where greedy algorithms fail to be optimal?
I guess there are cases where it fails, like when, for example, the higher, like the branches at like closer to the top of the tree have like a lower probability, but that sentence like going down from there like has like a higher probability. If that makes
Let's look at an example of that. So let's just look at let's say we just wanted to pick 2 more words for this, okay? The greedy algorithm would choose, why is life so hard? What is the probability overall of these 2 words ending this sentence, according to the language model? It's the multiplication of these 2 probabilities, right? We multiply this probability by this probability to get a total of just make sure, right, 0.08 for so hard. And there's a reasonable argument to be made that what we should be choosing is the path with the very highest probability. Do we have a path in here of 2 words that has a higher probability than 0.08? Someone
Like
else help me out.
Very
Yeah, Ben.
difficult.
Yeah, very difficult is actually better than so hard. So this is a 0.10, and this is very difficult. So this is an example where, and I think it looks like difficult is partially cut off there, is that right? But you get the idea. So very difficult is better than so hard, but unfortunately, so kind of masks the very, right? And we don't get a chance, if we just take the greedy approach, to find that there are higher probabilities later on. So we're going to look at some different ways of traversing this tree and generating text. But first, let's just go back and say, let's say we do pick one of these words. How do we then get the next part of the subtree? Does that problem make sense? What we're going to do? So right now, let's just say we did choose so. We got this probability distribution, and we decided, forget it, we're going to be greedy. So we're going to choose so. Now what do? We fed these 4 words into the RNN, right? The beginning of stream plus these 3 other words. We fed them in. We got our y hat sub 4. Now we need to use this RNN again. The RNN is a black box. The way the RNN is normal, well, in fact, as we did on Wednesday in class, right? When you call the RNN, you feed in a sequence, and it gives you back your y hats. So we have to feed in a sequence again. We could feed in, instead of 4 words, 5 words. We could start the RNN sort of from scratch, feed in. So we could. So we chose now, we chose so. What do we do now? We could take this RNN and feed in BOS Y is life so, and this would be x1, x2, x3, x4, and x5. We could, just like we did here, feed in a 0 for our h sub 0, and we'd now get back out y hat 1, y hat 2, y hat 3, y hat 4, and y hat 5. Of these, which do we care about?
Y hat 5.
We have y hat 5. That's right. And that now is going to give us these probabilities, and now we can choose to continue to use the greedy algorithm. Does this seem somewhat wasteful, though? As we add each chosen generated word, we're going to be making the sequence we fit into the RNN longer and longer. And we're redoing a lot of work, right? We would expect y hat 1, y hat 2, y hat 3, and y hat 4 to all have the same values in this call as they did in this call. So instead, we're not going to do this, okay? Not what we're going to do. Instead, we're going to take this output here. So we know we got out a h sub 4. Normally, we don't use it. We don't care about it. So we got out of the y hats, and we got the h sub 4, and often we just throw the h sub 4 on the ground. But instead, here's what we're going to do. So we chose so. We're going to feed in x sub 1 is so. We're going to, since we feed in 1 x sub 1, we're going to only get out 1 y hat sub 1. So x sub 1 is going to go in here. Y hat sub 1 is going to go in here. How are we going to ensure that y hat sub 1 here is identical to y hat sub 5 here?
We use h4.
Exactly. We feed in h4. If we feed in h4, we're going to get identical results, right? This is deterministic. Identical results, because we're not in training mode, right? In training mode, this might not be deterministic. We might have dropout and other sorts of things. But in evaluation mode, this is completely deterministic. So feeding in x sub 1 with a so, with the output of the RNN after having put in these 4, is identical to just feeding in all 5. So that's going to make this cheaper, right? In that each word that we generate, we only have to call the RNN with 1x and get out. We're going to actually call it with 1x and 1h and get out 1 y hat and 1h. And then we'll feed in that new h to the next layer. Does that make sense? So that's really important because that tells us how we are going to actually be navigating through this tree. We are going to get an initial probability distribution out. We're going to choose a word, perhaps greedy, or we'll look at other cases in just a moment that we can navigate through this tree. And then we'll take that word, we'll feed it into our RNN along with our saved hidden state. We'll get out our new y hat, we'll save the state that comes out, and then that'll give us, it'll reveal a new part of the tree. We can choose from there, we keep going until eventually, using this algorithm, greedily, we find an end of string or end of sequence. Any questions on that?
Or just from a naming standpoint, do we update the subscript of the y hat, or is it always considered y hat sub 1?
It's always y hat sub 1 because it's the first one that goes in. So we have to keep in mind this x sub 1 conceptually is really x sub 1 plus however many x's we've already fed in. So in this case, since we fed in 4, this is really x sub 5. Okay. So here's what I'm going to do now. I'm going to go ahead and erase everything having to do with the RNN. And we're going to work now just in form of the tree. Because we know where this tree is coming from, how we're generating it. And so now we can focus on navigating in the tree and producing our best sequence. Okay?